I am thrilled to announce the completion of my research. Not that anyone cares, but I gotta share it, right? Like, this is what you do. I tried to publish an article. It was rejected immediately. It's actually the fourth time, but the first three times, my research is crazy because, like, I get excited and I think that I've made progress, and then I publish stuff. I try to tell everybody, and then, like, I have to backtrack a little bit. I was wrong about this or wrong about that, and I guess that's just the way things go. But especially when you're an amateur like me, like I don't have any training. I don't know what's going on. But let's get into this. The universe is not expanding. Why is the universe not expanding? Why? Well, the reason they think the universe is expanding is because of the cosmological redshift. I've got the Doppler effect on the screen here. It's a graphic of the Doppler effect. Shows how light waves are redshifted on the trailing side. So if you're looking towards the object as it's moving away from you, you'll see a redshift in all the light waves, or sound waves, any waves. But this is why they think that the universe is expanding, is because when they look out at stars and galaxies, there's a redshift. But there's also another way of redshifting light, and that's through gravity. It's called gravitational redshift. Basically, as light is climbing out of a gravitational well, it gets redshifted, because depending on where the observer is located, there's a difference in the distance and time of the space close to mass. There's a difference. This is how gravity works. Space contracts and time dilates, and the more mass there is, the more contraction there is, and the more dilation there is, and this causes the gravitational redshift. Now, it's a little confusing because gravity is cumulative and its reach is infinite, so it's a little confusing, because all of these boundaries that we assign to objects aren't real. They're not real boundaries. An object is only an object because a human defines it as an object. In other words, the sun, if you just imagine, where is the boundary of the sun? Well, you could say that Jupiter is part of the sun, depending on where you're looking at it from. You could say that the sun is actually just part of the Milky Way. It just depends on the context. And so I think the correct term for this is nested gravitational wells. I think that that's probably the term that would get you the most amount of hits. This is at least in the closest region of what I'm trying to say. There's not that much research on it. Honestly, nested gravitational wells is considered a local effect and not a cosmological effect. I have no idea why they think this. It's because the reason they think this is because they think the universe is expanding and that the reach of gravity diminishes because the things are expanding away from each other. But this is just an assumption. We can also assume that it's gravitational redshift. Instead of assuming the universe is expanding without a reason, there is no known reason for the universal expansion. They can say dark energy all day long, but that just means I don't know. And so with gravity, you already have gravitational redshift. So if we assume the cosmological redshift is gravitational redshift, we're removing an assumption. Does that make sense? We're actually using less assumptions. And in science, the theory with the least amount of assumptions is the winner. I mean, the theory that matches reality is the winner, but it's, Occam's razor is tells you to, get rid of as many assumptions as possible. You want to eliminate all of those variables, those unknown variables. And dark energy is a giant unknown variable that they don't know what to do with. They can measure, but all they're measuring is the change in light in the frequency of light from the moment it was emitted to the moment it was observed. They're not actually measuring dark energy. So what they're measuring, though, is the gravitational field between the emitting object and the receiving object. It's like the whole of the gravitational field. And it's because, like I said, all objects are in nested gravitational wells. Every object is nested in the observable universe. And every object is nested in the scale that is slightly smaller than the observable universe. And every object is nested in a scale that's slightly smaller than that. And it just goes on and on and on until you get to galaxies and stars and atoms. They're all nested, and it's all one big happy family. In general relativity, they call it a unified manifold, or a single manifold. It just means that it's just one object. There's just one object. And these nested gravitational wells are when you're viewing only a portion of the object. Like, say, that's the wrong way to say it. If you are making an observation that is of a galaxy, and it's very short distance from you, or, relatively speaking, let's say that it's 1 megaparsec away, and you're looking at this galaxy, you're only looking at a small portion of the observable universe. It's just a small little sample. And so it has a very little bit of redshift. I forgot to mention this. The cosmological redshift is distance proportional. That means that the further the object is, the further away the object is, the more redshift there is. And this is why they think that it's not gravitational redshift, is because it changes. When a star is really far away, then it has a lot of redshift. Why would that be if it's the same size as a star that's close by? Well, it's because it's nested in a larger gravitational well. It's the same as if you're looking at the sun. Our sun, it has a small amount of redshift. Okay, it's whatever it is. It's a small amount. It's just going to be a tiny change in frequency. However, if you look at a galaxy, there's going to be more. There's going to be more gravitational redshift because that star is now inside of a galaxy. It's the same light. It doesn't change. There's nothing, no difference. It just depends on the observer's location. The further away you are, the more objects that contribute to the nested gravitational well. So, here's the Matryoshka dolls. This is the Russian Matryoshka. I think I'm saying that right. Russian Matryoshka dolls. These are awesome. This is the perfect analogy for the universe. It's like everything is inside of everything else, though. I mean, it's like the outer doll, the main doll. The biggest one would be the observable universe, and the smallest one would be an atom, I guess. Or actually, the smallest one would be the Planck length. If you just imagine it as each doll is a Planck length, and so you can draw an infinite, or not an infinite, you can draw, I've got the calculation right here actually. So this is the observable radius is 1.28 times 10 to the 26 meters, something like 13 billion light years. And then you have the Planck length. You divide the observable universe by the Planck length and you get 8 to the 60. So there's something like 8 to the 60 in each half of the universe, Planck length. So that would mean that there's something like 8 to the 60 spheres, dolls, you could say. That many dolls. And, it depends on how you draw this manifold, depends on your location and all this. You can draw. You can try. When I say draw, I'm model. You can model the observable universe like this. But in the past, they've denied static cosmology because cosmologists think that the universe would be unstable if you do it like this. If you just build the universe out of out of the cosmological redshift. In other words, the first assumption that you make is that the cosmological redshift is caused by gravitational redshift. Then you can work backwards and find the distribution of mass that is required for that. And the distribution of mass for this aligns perfectly well with observations. There's some argument depending on the knowledge of the person you're talking to with that statement, but this is absolutely a better way of distributing mass than the Friedman metric, because the mainstream cosmology method of doing it, the FLRW metric, it assumes homogeneity. And you can't assume homogeneity because the universe is obviously not homogeneous. It's homogeneous on the largest scale, but it's, that's kind of cheating. You're only doing one scale. And so you have to change mass density. Mass density is a scale-dependent variable. It is not a constant as the FLRW pretends it is. And there's also this argument of instability with static universes. I don't get this argument at all. It makes zero sense to me. If you just draw a line and use that for your radial coordinates, it's not going to be accurate for the first part of your metric, because you have local distributions. But as you get further and further, as your radial coordinate gets longer and longer, there's more and more symmetry, and so your assumptions can kind of start to lean on the cosmological principle a little bit, and you don't have to make perfectly accurate predictions. This is fine because this is exactly what the FLRW does. The FLRW metric, and when I say the FLRW metric, it's what I'm saying is this is the solutions to the Einstein field equations that they use for modern cosmology. And it's a metric that assumes the universe is expanding, it assumes the universe is isotropic, and it assumes the universe is homogeneous. And if you assume those things, then you have a scale factor. And the scale factor depends on the rate of your assumptions. But we don't need any of that. Because those are all assumptions that we don't have to make. We can just model the universe as it is. And if there's a problem with designing a metric that way, then I would propose that we use null geodesics. So you just follow the path of a light wave, and then we use that as the metric. That's as a reference line for our radial coordinates. If we do that, then we get rid of the stability problem, because we're actually using the geodesics. We're actually using the real physical causal path of the light wave. This is not. It's not a guess. Locally, you can assume that the mass is, it's going to be a star. It's an average star with an average galaxy and an average cluster and an average supercluster. We can make all these assumptions that the universe is, what's the word? It's going to appear the same for all observers. It's symmetrical, I think, is the appropriate word. Mainstream cosmology uses the words isotropic and homogeneous, but I don't think that those are accurate terms. In my opinion, I think the best way to say it is symmetrical. The universe is symmetrical, and it gets more symmetrical the larger it is. We're going to get to the good part. I'm already 15 minutes in, and this is basically just review for everybody that's subscribed. And I apologize. I'm getting there. I'm terrible at making videos. I don't like doing this at all. It's difficult talking into a microphone. Matter of fact, I'm going to take a break. Alright, so let's get into the meat of everything. I'm actually going to ask ChatGPT some questions here to help explain. ChatGPT, would you like to tell our listeners what the Hubble constant is?
The Hubble constant is a value that describes how fast the universe is expanding. In simple terms, it tells us how quickly galaxies are moving away from each other. This constant is crucial for understanding the rate of expansion of the universe and helps astronomers estimate the age and size of the universe.
And what's the rate?
The rate of the universe's expansion, represented by the Hubble constant, is usually measured in kilometers per second per megaparsec. Currently, there is some debate among scientists about the exact value, but it is generally estimated to be around 70 kilometers per second per megaparsec. This means that for every megaparsec, which is about 3.3 million light years, that you look out into space, galaxies are moving away from us at about 70 kilometers per second faster.
But there's also another way, another method, another set of units we can use. Hertz, right?
Exactly. The Hubble constant can also be expressed in units of inverse time, like per second or hertz. When expressed this way, it gives an idea of the rate of expansion in terms of how quickly space itself is stretching over time. This can be useful in certain cosmological calculations and provides another perspective on how the universe is expanding.
But it may not be expanding. We don't have to jump to conclusions. We're just talking about the redshift specifically.
That's right. The Hubble constant is based on observations of the redshift of galaxies. Redshift occurs when the light from distant galaxies is stretched to longer wavelengths, which makes it appear more red. This redshift is interpreted as evidence that galaxies are moving away from us. And the farther away a galaxy is, the faster it seems to be moving away. This observation supports the idea that the universe is expanding, but it's always good to explore all possible explanations and not jump to conclusions too quickly.
Yes, because it could be caused by gravitational redshift from mass being nested in gravitational wells.
Exactly. Gravitational redshift is another phenomenon that can cause light to shift to longer wavelengths. This happens when light escapes from a strong gravitational field, like that of a massive object. While gravitational redshift does occur, the redshift we observe in distant galaxies is generally attributed to the expansion of the universe, rather than gravitational effects. However, considering all possible explanations is important in scientific inquiry.
Yes, because nested gravitational wells is definitely there's definitely a way to align the distribution with the Hubble shift using nested gravitational wells. Correct?
There is an idea that gravitational wells could influence the redshift of light. However, the specific pattern of redshift we observe across the universe fits better with the model of cosmic expansion.
No, that's not necessarily true. The redshift can be aligned if you just assume that it's gravitational redshift. The problem is that cosmologists don't think that a static universe is stable, but you can just assume the Hubble shift is gravitational redshift and then draw you draw the density from that.
That's a fair point. Some alternative theories do explore the possibility that the observed redshift could be explained by gravitational effects rather than cosmic expansion. These theories suggest that the redshift could be due to light traveling through regions with varying gravitational potentials. However, the standard model of cosmology, which includes
we know what the standard model of cosmology says. It says that there's dark magic everywhere. But let's change subjects for a second. Would you say that every mass density has a corresponding Schwarzschild radius?
Yes, that's correct. Every mass has a corresponding Schwarzschild radius, which is the radius of a sphere such that if all the mass of an object were compressed within that sphere, the escape velocity from the surface would equal the speed of light. This is the basic concept behind a black hole. For any given mass, the Schwarzschild radius can be calculated, and it provides a way to understand the relationship between mass, gravity, and the curvature of space-time.
And we can also use mass density as well.
Absolutely. You can think about it in terms of mass density as well. If
Okay,
you know the density of an object and the total mass it contains, you can determine the size it would need to be compressed to reach its Schwarzschild radius.
but
If the density
it doesn't necessarily have to be compressed to produce a Schwarzschild radius, does it?
You're right. The Schwarzschild radius is a theoretical boundary. If an object's actual physical size is smaller than its Schwarzschild radius, it would form a black hole. However, the concept of the Schwarzschild radius can be applied to any mass, regardless of whether it's actually compressed to that point or not. It's a useful way to understand the relationship between mass, gravity, and the potential for an object to become a black hole.
And the Schwarzschild radius follows an interesting pattern. It gets longer with more density.
Yes, that's correct. The
Or
Schwarzschild radius
more mass.
increases with the mass of an object. Specifically, the Schwarzschild radius is directly proportional to the mass. So as the mass increases, the Schwarzschild radius also increases. This means that more massive objects have larger Schwarzschild radii.
Yes, exactly. That's a wonderful way to say it. Okay, now give our viewers a an idea of Hawking radiation. What is Hawking radiation? How does it
Hawking
form? Go ahead. Sorry.
No problem. Hawking radiation is a theoretical prediction made by physicist Stephen Hawking. It suggests that black holes can emit radiation due to quantum effects near the event horizon. This radiation arises because of virtual particle pairs that constantly form near the event horizon. Normally, these pairs would annihilate each other and disappear. However, near a black hole's event horizon, one particle can fall into the black hole, while the other escapes into space. The escaping particle is what we observe as Hawking radiation. Over time, this radiation causes the black hole to lose mass and eventually evaporate. It's a fascinating concept because it shows that black holes are not entirely black and can emit radiation, which was a groundbreaking idea in theoretical physics.
And tell us about the wavelength of that radiation and how it relates to the Schwarzschild radius.
The wavelength of Hawking radiation is related to the temperature of the black hole, which in turn depends on the black hole's mass. Smaller black holes have higher temperatures and thus emit radiation with shorter wavelengths. Larger black holes have lower temperatures and emit radiation with longer wavelengths. This relationship is inversely proportional, meaning that as the Schwarzschild radius increases, the temperature decreases and the wavelength of the emitted radiation increases. In essence, the larger the black hole, the longer the wavelength of the Hawking radiation it emits.
Yes, and there has been some talk that the cosmic microwave background radiation could be Hawking radiation because the Schwarzschild radius of our universe is the same size as the observable radius. And so there was some I don't know if there was ever anything published, but I have read a few things on the internet that the CMB was considered as Hawking radiation by a couple of people, but the temperature is way too low.
That's an interesting point. The cosmic microwave background radiation, or CMB, is the afterglow of the Big Bang and fills the universe with a nearly uniform temperature of about 2.725 Kelvin. While it's true that some have speculated about connections between the CMB and Hawking radiation, the prevailing scientific understanding...
Yeah, we don't care about the prevailing scientific understanding. I'm going to turn him off and then go to... This is my calculator that I've made. And so what this does is it's going to tell us everything depending on whatever inputs we have. Let me refresh this. I don't want that. Okay, so the Hubble constant, this is the, I have 2.33 times 10 to the negative 18 hertz. So that is something like 72, I think, kilometers a second per megaparsec. And so that gives us a Schwarzschild radius of 1.2, 8 times 10 to the 26 meters. This is so that I can... We'll get into this just a second. Let's put the Schwarzschild radius in here. So if I put the Schwarzschild radius in here, have I described this well enough? I think I have. It's all the inputs for these two, or this is all the outputs for these two inputs. So I put the Schwarzschild radius in here. This is the 1.2. The density for this is the observable universe. This is if we're viewing a star, or we're looking at something that is 1.286662998, whatever, times 10 to the 26 meters away from us. It's going to have an extreme amount of gravitational redshift. It's going to be virtually you're not undetectable. Is virtually undetectable for a lot from a star is going to be so gravitational redshift. However, the Hawking radiation is not coming from a star, so it's going to be blue shifted. Okay, it's going to be blue shifted. Now, this says 16 degrees, but this is not a valid. This is not a valid answer. This should be 0 or infinite, because it's just JavaScript sucks. This took me years to develop this calculator. It wasn't until I had ChatGPT and Claude until I was able to make something like this, because I didn't know why JavaScript sucks so bad at math, but it's not precise at all. And so this should be, I can't get rid of it. I don't know. It should be 0 or infinite, which sucks that I can't get rid of it, because right now it's at 16 degrees. However, if we go 1 Planck length, so I'm going to subtract 1 Planck length from this, okay? This is literally the Planck length, 1.6 whatever times 10 to the negative 35. If I subtract that, we get 2.7 degrees Kelvin. Boom! I don't know if you understand that. I don't know how many people will get that, but to me, this is phenomenal. Okay? This is phenomenal because it validates everything I've been saying for 16 years. Now, science, mainstream academia, they're too worried about pronouns and this is true. The paper I submitted, the dude responded back and said, I'm sorry, but we're not interested in publishing your paper. And he had his pronouns in his bio. And, I got no problems with those people, but, it just gives me an idea of where your brain's at, Anyways, this is it, people. I don't know what else to say. Let me explain it one more time. So, you have each distance has an amount of gravitational redshift, because each distance includes a portion of the universe. Okay? And so if we just you can just take any distance, whatever I call it the radius. This is the radial coordinate. This is the radius, the radial coordinate in general relativity. So however, it's, for me, I like to use null geodesics, so it's the path of the light wave. That's the best way to explain it, but I don't care. In my opinion, you can just draw a line. So long as it's a line that is sufficiently long enough for symmetry to start taking place, in other words, 1-2 megaparsecs long, then this cosmological model will take effect. You have an amount of mass in that volume having the radius of the line you drew. There's an amount of mass in that. That amount of mass creates an amount of gravitational redshift. And so let's just put in, I'm going to restart this. We'll start back at the Planck length. I'm going to put in 100 megaparsecs. Let's just go to 1 megaparsec, actually. So we're at 1 megaparsec. The gravitational redshift, this is the Z. It's very low at this. It's 72 kilometers a second per megaparsec. That's what it is. Now, this is not a Schwarzschild radius, so we don't have to worry about Hawking radiation, because the Schwarzschild radius is 1.28. As we increase the Schwarzschild radius doesn't change. The reason the Schwarzschild radius doesn't change is because we're using the Hubble constant to define everything, to define our density. And so that's why, like, I mean, it's taking the whole distribution into account here. At something like this distance, this is very close to the observable radius. We have an extreme gravitational redshift, which is how fast it appears to be moving away from us. It's something like what is this? 14 million. Yeah, it's really close to speed of light. Speed of light's 299,792,458, and this is 14 million. So it's or 143 million. At the observable radius, we have this much more gravitational redshift. Oh, let's minus 1 megaparsec. So we're almost complete. Oh, we're already past. I'm past. Calculator broke. Something broke. Okay. So if a star is 1 megaparsec away, we have this is the amount of gravitational redshift. That's extreme. So 45 is extreme. Like, I don't even think we've ever observed anything at that distance. This is Z equals 45. So I mean that is absurd. Like that is James Webb stuff right there. And so it looks like it's traveling at nearly the speed of light. Now, we increase 1 megaparsec, and we're going to minus 1 Planck length. So we're as close to the Schwarzschild radius as possible. As absolutely. If you go any further, you are the Schwarzschild radius. And it is the coordinate singularity. This is just a coordinate singularity. It's not a real black hole, okay? That's just the nature of black holes. Is like a ChatGPT explained earlier. As the radius increases, my heater kicked on. I didn't know that. My heater kicked on, and that probably ruined the broadcast. I wonder how long that's been on. Anyways, what was I saying? The Schwarzschild radius, as the mass increases, the Schwarzschild radius increases as well. And if we go 1 Planck length from the Schwarzschild radius, all of that mass that's in the observable universe, that's 1 Planck length from the observable universe, creates this gravitational redshift. Okay, this is actually the true calculation. It's almost 2 times 10 to the 30, and that amount of blue shift for this Hawking radiation. The Hawking radiation is very low. See, the temperature, because the Schwarzschild radius is huge, the temperature is extremely low. But the cosmic microwave, or the amount of blue shift, raises the temperature to 2.7. It's amazing. This is amazing. Anyways, have a good night.